We've been saying that we get our interference of waves, our standing waves, when we have waves created by a source coupled with waves reflected from a boundary. Let's talk now about that nature of that boundary and what happens. So let's ask what happens when a pulse hits a fixed boundary, and we're going to assume our boundary is ideal. And by ideal, we mean we're not going to get any energy lost. So what I've got playing in a little simulation there is a pulse put out by the source. So there it goes, moves down the line, and it hits a clamp, a fixed boundary. You can see what happens. It turns upside down. So when a wave hits a fixed boundary, it reflects and it inverts. So that's the first thing we notice. Let's see if I can write that on there. So our wave inverts. So it certainly does inverts. If it inverts, it means that there's a pi phase shift. That very bad handwriting says phase shift. Okay, so pi phase shift. And now let's talk about why does it invert? And that's kind of an interesting idea. We can apply Newton's second law. So let's look at our pulse and let's look at this set of pictures now. The pulse comes down the line and let's look at what happens when it gets to the wall. The rope is touching the wall, so the rope pulls up on the wall. There's the force of the rope on the wall. I'll say FW for the force on the wall. Newton's second law says that for every force, there's an equal and opposite force. So there's a downward force on the string or on the rope. So there's the force on the rope. If there's a downward force on the rope, by Newton's third law, it says Newton's third law tells us that the force is downwards. If there's a downwards force on the rope, it means there's going to be an upside down pulse. So that's where the inversion comes from. The wall pulls down on the rope, it makes an upside down pulse, which goes down the line. And if something flips completely over, we call that a pi phase shift. You might once in a while see 180 degrees, but pi is more often. Okay, there's our ideal boundary. Next we'll look at, or that's our fixed boundary. Next we'll look at the free boundary, so it's not fixed at the wall. So for a free boundary, in our simulation we've got the string tied onto a ring on a pole. We're going to assume everything here is frictionless, it can move up and down without falling. Let's not ask the question why it doesn't fall down in the first place, so let's just put a little bit of magic there. So our frictionless boundary right here, the pulse comes in, and then let's see what happens at the boundary. It lifts and then it falls. So the lifting and the falling makes a pulse that's still upright. So our reflected pulse is upright. So the reflected pulse stays upright. If it's upright, there's no phase shift, or I suppose you could say a zero phase shift. So if we have a free boundary, and again, ideal, so there's no energy lost, it lifts and falls and it leaves us with no phase shift or an upright boundary. Now, of course, this begs the question, what if it's not exactly free and what if it's not exactly fixed? What if it's kind of somewhere in the middle? Let's put that one next. So let's ask about an intermediate boundary. For something like this, let's think of a rope that has one end that's really heavy and this other end, the other half, is really light. So like a thick string tied onto a small string. What would happen to a pulse going down that rope? Well, what happens is there's still a boundary. So there is something still right here. Let's see. There is still something right here. And the thing that's right here, it's partly like still a string, but it's partly like a boundary. And the kind of boundary this is going to be like, as we go from heavy to light, is it's like a free boundary or a free end. So it's still a string, but it's also partly like a free end. So what happens is that part of the wave reflects. So we get reflection. So reflect, and part of the wave transmits. So it partially transmits because it's still a string, and it partially reflects because it's a boundary. The reflected wave stays upright because it's more like a free end where it goes from something big to something small. So our reflected wave is upright. And what about the transmitted wave? Well, we could ask about the speed of the transmitted wave. If you remember that v is the square root of t over mu, then our transmitted wave in this second part, it's got a small u, so it gets a bigger v, so it speeds up. And the last thing we might point out is if we thought about the amplitudes of these two waves, before the pulse has a certain amplitude, afterwards we have two pulses, the energy would have to split over both those pulses. Because it splits and the energy of each of the two pulses would be less than the initial one, so the two amplitudes would be smaller than the initial because energy is conserved. Okay, that's what happens if we go from a heavy string to a light string. It's like a free end and we get the wave motion. Let's ask what happens the other way. What if we go from a light string to a heavy string? Well, in that case, we have kind of the same deal. We still have a string, so some of the wave is going to keep on going, but we also have a boundary. And because we have a boundary, we're still going to get some reflection. This boundary goes from a light piece of string to a heavy piece of string. That makes it like a fixed boundary. If it's like a fixed boundary, then our reflected wave will come back inverted. And our transmitted wave will still be upright because that wave is still going down the line. But since v equals root t over mu, and our mu is bigger as we go to a heavier rope, this wave is going to slow down. So that talks about our boundaries and what happens at the boundaries. An interesting application about this I like to think about would be an application with light waves. So if you pick up your cell phone, don't light it up, just look at it with the back screen. If you look at it with the black screen and you look at the glass, what do you see? I would say you probably see yourself. That's what you should see anyway. So there's reflected light and you see yourself reflected. But now let's think about the reflection and the transmission together. If you press the button to light up your phone, now you probably see two things. You see yourself in the glass, but you also see your background picture, and for me it's a picture of my cat, but I can see both things. So I can see myself because part of the wave is reflected, but I can see the picture of my cat because part of the wave is transmitted through the glass. So this sort of transmission and reflection together, it happens all the time, and we're going to think about it quite a bit. Maybe as one question I'll give you as a thought question, it'll be about why do we see different colors in bubbles? Maybe we'll think about some things like that too. Anyway, we'll think about that. The handwriting in these slides were pretty bad, so I may actually type up some additional notes to go on top when I post the after class slides.